simple Bronsted-Lowry acid-base equilibrium reaction will always involve the buffering acid reacting with the buffering base to produce the buffering acid and the buffering base. Because the buffering acid will be the strongest acid in high concentration in the system, and the buffering base will be the strongest base at high concentration in the system. Acetic acid acetate ion buffer results in this as the main acid-base equilibrium reaction. And this reaction, in fact, takes place. But it does not lead to any chemistry that's meaningful. At least not from a pH standpoint. Leads to no net change in system composition, nor does it give a handle on system pH. Remember, when you need a handle on system pH, you must examine one or more reactions which involve what? Hydronium ion or hydroxide ion. That's it. That's what pH is about. pH, negative log base 10 hydronium ion concentration, which by default gives you a handle on hydroxide ion concentration because of Kw and pKw. Question 1842. We'll talk about this in brief. You will complete the analysis and solution for question 1842 tomorrow in discussion class. We shall now lay foundation for such. Imagine treating 5.0 milliliters of deionized water with 5 drops of half molar to 2 significant figures hydrochloric acid solution. This will, of course, lead to a significant reduction in pH of the water. Because of the moles of hydronium ion you will add to the water by having treated with the 5 drops of the half molar HCl solution. Now, to play this game, you need to consider inventories from a quantitative standpoint, which means you need the volume of a drop. For aqueous systems, that's about 0.05 milliliters. Do you remember determining such in 2045 lab? It's handy. Hey, in 46 lab, you are oftentimes required to deal with small volumes of various solutions. Say a half milliliter. What do you want to do? Get out the 10 mil graduated cylinder, scrub it, rinse it, all that stuff, and then try to reliably measure a half milliliter of the solution, and then transfer the half milliliter, recognizing that water solutions stick to glass. Glass is hydrophilic, water liking, electrically speaking, so all the liquid won't come out. That's not the way to do it. That's too damn clumsy and inefficient. You want a half milliliter of a water solution of something? Count out 10 drops. Bing, 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 bing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you got your half mil all done. That's the way to do it. Indicating why this information is handy. In any case, back to 1842. From this, you will do the arithmetic to figure out the hydronium ion concentration for the deionized water, 5 mils after it's been treated with the 5 drops of the HCl solution. For those of you who wish to tackle this before tomorrow, which you should do, you'll get 0.024 molar. And we might as well label this 0.024 molar HCl solution. Because one way to look at this mixture is to imagine taking 5 drops of this solution and diluting it, because all you added was solvent. Okay? This information tells us that when we proceed to the second part of this question and now start with 5 milliliters of half molar acetic acid solution and treat that with 5 drops of half molar HCl, that the hydronium ion concentration in this solution is at least what? It's at least that. Because now you're combining 2 acidic solutions. One which, after the dilution factor, this with the 5 mils of that, gives you this. Call it, if you want, instead, nothing wrong with this. But we can instead call it 0.024 molar hydronium ion, because that's what you're looking for in this system, is what's the solution hydronium ion concentration. The $64 question regarding this issue is, after I took my 5 milliliters of half molar acetic acid, with which you've had experience, considerably so by now, by way of lecture chat and by way of work you've done in lab. You remember the approximate pH of half molar acetic or hydronium ion concentration? You remember the approximate hydronium ion concentration or pH for 1 molar acetic? Since you did this in lab, assignment 1. Anybody remember? What's the pH? 1 molar acetic to 1 sig fig is 2.4. With your colorimetric analysis, if you did the experiment properly, you should have got 2.4, something close to that. Maybe 2.3, 2.5. Because when you looked at the color of the 1 molar acetic treated with the methyl violet indicator, you probably saw it to show a shade of this blue-violet coloration that your eyeballs should have suggested was about halfway between the 2.0 pH standard, which shows a distinct blue with methyl violet, and a pH 3.0 standard, which with methyl violet shows a distinct violet blue. But the 1 molar acetic acid would have had a violet cast that the pH 2 standard doesn't have, that's just blue. And the 1 molar acetic acid would have had a greater blue cast in its coloration compared to the 3.0 standard, which is more violet in color than the 1 molar acetic acid on treatment methyl violet. Anybody remember this? We just did this. I mean, what, a week ago? Is that already ancient history? You already chucked it out of your noggin? Don't do that. You know by now, I hold you responsible for every doggone bit of work you've done. And that's included. How about that? Now, if you're not in the lab, it matters not, because for any molarity of acetic acid, you know now how to calculate the hydronium ion concentration. So what? So back to this issue. The equilibrium reaction, which I have on the board, of course, is alive and well in the half molar acetic acid. All right? And at the instant at which you take this half molar acetic acid and start dropping in the half molar HCl solution, at that instant, what happens to this equilibrium? It's killed. And since you added a component of the equilibrium, specifically this component, either this reaction or this reaction has got to occur to get this thing back to equilibrium. Which of these reactions will occur on this treatment? Right to left or left to right? Right to left. What is this telling you about the extent or degree of ionization of acetic acid molecule in the system after having treated with this external source of hydronium ion? Have you enhanced the degree of ionization, extent of ionization of acetic acid, or retarded it? Retarded it. Which means, whatever the ability was of acetic acid in the half-molar acetic acid solution by itself to react with water and make hydronium ion, that has been reduced. Its ability to react with water and make hydronium ion, because you added this, has now been reduced. The question is, to what extent has it been reduced? More specifically, is it possible that this solution, right here, this solution, the half-molar acetic acid with the 5 drops of the half-molar acetic HCl solution been added. It's already been added. Is it possible that this solution also has this hydronium ion concentration? And the answer is, you bet that's possible. If the ability of acetic acid has been retarded to the extent that to the thousandths place, the ionization of acetic acid no longer contributes measurably to the system hydronium ion concentration, then the acetic acid solution, after treatment with the 5 drops of the half-molar HCl solution, will have this hydronium ion concentration just like the water treated with the HCl solution. And what you're going to do tomorrow in discussion class, and if you really want to get ahead of the game, you're going to do this before you go to discussion class tomorrow. Maybe I'll tell the discussion instructors at the start of discussion class to say, you, and you go to the board and write the answer to this problem on the board. And if you can't do it, 2,000 points off the exam on Thursday from the first question. There's only one rat in here. That's me. Let me show you what you have to consider in case you're puzzled by this. Let's write it over here. I don't have room over there. There's the equilibrium constant expression, chemically speaking. And I notice a lot of you show me this when you come to the office and ask questions about this stuff. When you write a Ka value or a Kb value, what do I usually see you write first? X's. I don't want these damn X's. I want you to know, I want you to convince me that you know what the chemistry is that you're dealing with. And until you do that, I don't want to see any X's. Because X to me means you don't know what you're doing. You're just trying to follow a recipe. We don't do that anymore. That game is gone with 2045. Goodbye forever, goodbye. Now you have to understand. But you know that now, don't you? So I'm trying to see to it that you're in this understanding mode before Thursday. So you do well. That's what I want. The more top scores, the happier I am. And I've already commanded you to make me happy. Now then, for this system, the only source of acetate ion will still remain as the ionization of acetic acid. But now there's 2 sources of hydronium ion, right? the added hydronium ion from the HCl solution, which winds up producing a molarity of 0.024, plus how much?
From the acetic acid.
In terms of the components of this system, the equilibrium molarity of hydronium ion will be recognized now as 0.024. That's what you produce by treatment with the HCl solution. Plus what? I don't want to hear X. Plus? Plus the molarity of what? You've got to let this reaction equation talk to you. Let me get all this scribble out of the way. The reaction has occurred. We're now back at equilibrium. We're trying to find out the hydronium ion concentration. We know this is at least 0.024. This is whatever it is. And this is going to be, the hydronium ion concentration is going to be, let's write it here, H3O. Let's get this damn thing out of here. Equals 0.024 plus what? Let this thing talk to you. Does this reaction not tell you that as acetic acid reacts with water, per each acetate ion species produced, what else do I make? Right? So if I do this, I got it. Is that right? Here's my external source of hydronium ion. Here is the hydronium ion produced by this reaction. Right? Let this thing talk to me. And of course, the equilibrium molarity of this will be what? Less what? Acetate ion. Material balance, right? So now you know what you got to deal with. You're going to take this expression. For hydronium ion, you got 0.024 plus acetate ion. For acetate ion, you got acetate ion molarity itself. And in the denominator, you got 0.050 minus acetate ion. Actually, you should adjust this somewhat because of a minor dilution. Because you up the volume a little bit by adding the 5 drops. Right? But it's going to be still about this. It's all right about 0.50.
Is that after you add the 0.5 HCl? Because I thought the reaction would go that.
The reaction is going this way.
So why are you adding that?
Well, that's still my initial molarity. I don't know what it is. Okay?
But you're subtracting from over there. Shouldn't you be adding to that side? The reaction's going to
Well, if this goes this way, okay, because clearly this is going to have a measurable acetate ion concentration in it. And the only source of acetate ion is the reaction of this. So we have to do this. Now, I mean, you're going to find out what the arithmetic you're going to do. So now if you want to resort to x's, you got this to operate on. So, if you find that the value for x is less than how much, the hydronium ion concentration for this solution will in fact be 0.024. these days, I'm going to come in here and I'm going to chop every one of these damn things off of here. All the time with this stuff. It's falling apart. If X is less than how much? Then the hydronium ion concentration will in fact be 0.024. What's X got to be smaller than? So that 0.024 plus X is in fact 0.024. What? Is this correct? Is this correct? You got to let these numbers talk to you. Is this correct? No, because X could be 0.001. And if I add 0.001 to this, I get 0.025, don't I? So after rounding, X has got to be less than this. Put another way, in this decimal place, right here, the thousandths decimal place, what's got to be the value for X? 0. Who cares what's over here? As long as it doesn't round to change this to 1. So if you want to be really careful with this, X has got to be less than this. That better? Because if I have, for example, this value for X, and I got to round it to this decimal place, I get 1. So if you find X is less than this is correct. And that's what you're going to find. So how is this system and its behavior comparable to that of a buffer? Can you operate on this with X squared over M sub I minus X? For this system, the hydronium ion molarity and the acetate ion molarity, anything close to each other? So how could you write X squared in the numerator and have it mean anything? And it all follows from, guess what? Inventory. If you know what the heck's in the system, you can't go wrong. And if you don't pay attention to the chemistry, you will go wrong. That's it. All right? As I said, you'll finish this up tomorrow. As necessary, you now know what to do, and also tackle 1843. With that, I go to page 1837. And expose you to another problem, which really is a takeoff from what we've just done. In a moment, you'll see why. The example that's considered in the notes is that of imagining you go to the laboratory and you see a solution which has this label on it. The question is, what's the pH? Now, for each and every HCl solution that we have so far considered, how has the hydronium ion concentration compared to the label on the bottle? M sub I. They've always been equal. Are they equal for this solution? No. Because if you're going to tell me this solution has a hydronium ion concentration of 3 times 10 to minus 8, then you're also going to tell me this thing has a pH greater than 7, and how the hell can an acidic solution be basic? Don't ever stop thinking about the chemistry. Once you do, you lose. Game over. Point. For any very dilute solution, very dilute, You're always going to have to pay attention to the solute and its chemistry, and of course the numerical label on the bottle, plus the ionization of water for any very dilute solution. Now, water reacting with water will in fact contribute measurably to the hydronium ion concentration for the solution, or hydroxide ion concentration for the solution. This is worked in detail in the notes. So let's look at question 1844. Now I'm in the lab and I see a bottle that bears this label. 5 times 10 to minus 8 molar sodium hydroxide solution. Well, if I know any chemistry at all, and I recognize that water is my solvent, I took water and I dissolved in it a very, very small quantity on a per liter basis, namely 5 times 10 to minus 8 moles of sodium hydroxide. But this stuff is a base, so I know damn well I made a basic solution. So if I argue that the hydroxide ion concentration in this solution is 5 times 10 to minus 8 molar, I lose. Because 5 times 10 to minus 8 molar hydroxide ion for a solution is an acidic solution. Because the hydronium ion concentration in that solution is 2 times 10 to minus 7 molar. And that's bigger than 5 times 10 to minus 8 molar. And it's bigger than 1 times 10 to minus 7 molar, which is acidic. So don't go telling me a basic solution is acidic. And every now and then I have a student say, look, that's what my calculator showed me. I give the calculator an A. Because the calculator did correctly the arithmetic it was asked to do. What do you think I give the student? Z. How's that? Isn't Z lower than these other bad grades? So you have to realize that when we are examining this equilibrium for this solution, how many sources of hydronium ion do we have? For this solution, how many sources of hydronium ion? 1. It's this reaction. How many sources of hydroxide ion? 2. This reaction and this solute. So there's the comparison of this to that. Because here we were asking the question, based on this extra source of hydronium ion, the added HCl solution, plus the ionization of acetic acid, is it the case for this solution that the acetic acid didn't contribute measurably to the hydronium ion concentration? And that's true, which you will find out when you do the arithmetic I asked you to do. All right? Back to this. This, if you wish, we'll call it X, simply because X is quicker and faster to write than hydronium ion molarity. What is this? What is it? I got 2 sources. This source gives X. This source gives 5 times 10 to minus 8. So I add them together. Okay? That's it. And now I have to solve. For this solution, I can ask what's the pH, what's the pHO, what's the hydronium ion concentration, what's the hydroxide ion concentration. I can ask all these questions. They're all the same question. Really. How do I solve it? I got 1.0 times 10 to minus 14 equals X times this. Well, if I expand it, I see it's a quadratic. I'm not fooling around with any quadratic recipes. Get that trash out of here. That goes with the book I kick out the door. I want to understand chemistry. That's where it's at. And the first thing I realize is, in thinking about the chemistry of this solution, is remember it's very damn dilute. And X represents the hydronium ion concentration. So given that this solution is very damn dilute and is very mildly basic, I know the hydronium ion concentration is very close to what number? 1 times 10 to the minus 7. It cannot be larger than 1 times 10 to the minus 7, but it can be smaller. But if it is smaller, it ain't going to be a whole lot smaller. So to solve this, I'm going to speculate on a value for X, which represents the hydronium ion concentration, that's close to 1 times 10 to the minus 7. Pick me a value.
2 times 10 to the minus 7.
I'm listening.
2 times 10 to the minus 7. 2 times 10 to the minus 7.
I had a suggestion of 2 times 10 to the minus 7. I just made the solution acidic. Can't do that. Pick me a value that's close to 1 times 10 to the minus 7. 9 times 10 to the minus 8. That's reasonable. We're only allowed 1 sig fig because I only got 1 sig fig on the bottle label. All right, let's try that. 9 times 10 to the minus 8. And watch out. 9 plus 5. Now comes the next watch out. What's 9 times 14? Now I don't want any buttons pushed. What do I get? 126? Well, if I round that, I get 1.3 times 10 to the minus 14, which is a little bigger than kW, isn't it? So there might be a better answer. So pick me another trial value for X, which is either 1 times 10 to the minus 7 or a little bit smaller than 9 times 10 to the minus 8. Which way do you want to go? Got to be smaller. Because this is telling you, the bigger I make X, the bigger I'm going to get for this product. So I'll go to 8 times 10 to the minus 8. What's 8 times 13? 104. Which is 1.0 times 10 to the minus 14, isn't it? Well, just to be sure I got the right answer, I'll put in 7. That gives me 7 times 10 to the minus 8 times 12 times 10 to the minus 8. What's 7 times 12? So what's the answer for X? 8 times 10 to the minus 8. Done. With that, you can get the pH, hydronium ion concentration, which you now know. It's 8 times 10 to the minus 8, and hydroxide ion concentration. All right? Now, page 1839. Take a look at page 1839 as we discuss this, because practically speaking, I'm not going to write anything on the board because what you need to know is on this page. And I see no reason to repeat it. Also, let me remind you that the upshot of what you see on page 1839 is on the information sheet. Specifically, to what extent or degree can I get a weak acid to ionize or a weak base in water solution by progressive dilution? Because we have recognized that if you have a water solution of a weak acid and you continue to make it ever more dilute, you increase the extent of ionization. That we know. Same for a base, weak base. So we'll start with this question. For a very, very dilute aqueous solution, what is the hydronium ion concentration? 1 times 10 to the minus 7. Perhaps 1.0 times 10 to the minus 7. Perhaps 1.00 times 10 to the minus 7. Now ultimately I'm going to get to a point, if I keep on adding significant figures, where it's going to be smaller than the value I cite. Like instead of 1.000 times 10 to the minus 7, it might be 0.999 times 10 to the minus 7. But that's got 3 sig figs, and it's damn rare that I'm in the laboratory, except for quantitative analysis class, when I'm dealing with solutions where concentration values for any contained species needs to be considered beyond 2 sig figs. For just about all cases then we're going to look at infinite dilution, when the solution is extremely dilute. Hydronium ion molarity, hydroxide ion molarity will each be 1.0 times 10 to the minus 7. I don't care what solutes you got. I mean, after all, if I take a swimming pool full of deionized water and I put in 1 molecule of HCl, I know the HCl ionizes. You think that's going to change the hydronium ion concentration for the swimming pool, given I only put in 1 molecule? I don't think so. Not measurably. Next, which again is shown on this page. If the value for Ka or Kb is bigger than 1.0 times 10 to the minus 7, then by progressive dilution, I can get this acid, or base as the case might be, to ionize to an extent by dilution greater than 50%. But if Ka or Kb is smaller than 1 times 10 to the minus 7, I can't get to 50%, let alone greater than 50%. Do you see why? Here's this reaction. Ka for acetic acid is 1.8 times 10 to the minus 5. So with the max percent ionization recipe that you see derived on this page, and you see it given to you about 2/3 of the way down the page, which is also on the information sheet, you can get max percent ionization for acetic acid. All you need to know is its Ka value based on dilution. It's Ka over Ka plus 1.0 times 10 to the minus 7. That, of course, is the hydronium ion concentration given to the solution as a consequence of its being extremely dilute. So let's take a look at this very same equilibrium reaction. Pardon me, not this very same equilibrium reaction, but the corresponding equilibrium reaction for the conjugate base of acetic acid. Now, given that Ka acetic acid is 1.8 times 10 to the minus 5, without even doing arithmetic, we know that Kb acetate ion, the conjugate base of HAC, is smaller than 1.8 times 10 to the minus 7, 10 to the minus 5. It's in fact 5.6 times 10 to the minus 10, which happens to be equal to Ka for ammonium ion. So the K for that thing at the bottom is 5.6 times 10 to the minus 10. And I have stipulated that by dilution, you cannot get acetate ion to react with water to an extent which even gets close to 50%. Do you see why?
H2 is a stronger base than acetate ion, so it's going to H.
Well, if you had this thing ionized 50%, okay? If by this reaction this went 50%, then how would the molarities of these compare? If this ionized 50%, how would the molarities of these compare? They'd be equal and equal to half of m sub I, right? 50% of the, and this would still be, I mean, this would now be half of m sub I. Okay? What do you think about the tendency for H plus exchange to take place between these two? If you've got these at a molarity which is comparable to this, do you think you can make these at a molarity comparable to this? Hell no. It's too reactive. Can't be done. Okay? But if you apply that logic to this, you'll see why this one can go beyond 50% and this one can't. I want you to think about it. That's what counts. But as I said, the arithmetic upshot of this analysis, or using the formula that says Ka times 100% over Ka plus 1 times 10 to the minus 7, or Kb times 100% over Kb plus 1 times 10 to the minus 7. That's on the information sheet. Use it as necessary. The derivation is on this page. What we're going to look at on Wednesday, in conjunction with what you do tomorrow, and all the stuff we've so far done, is fair game for the first exam. And let me tell you specifically, on Wednesday, we are going to look at, in detail, calculation of the hydronium ion concentration for water solutions of sulfuric acid. How does sulfuric acid differ from the acids we have been discussing so far? It's diprotic. Under appropriate conditions, a sulfuric acid molecule can give you 2 H pluses as opposed to just 1. That on Wednesday.